I want you to think about the last time you got a paper cut.
Oh, yeah. The worst.
Right. Just a tiny, annoying slice on your finger. You probably winced, pressed a tissue against it for a minute, and then completely forgot about it by lunch.
Yeah, usually.
But in that exact same week, you might have been stressing out about taking a long-haul flight. You know the feeling, anxiously doing those little ankle circles in your economy seat.
Terrified of getting a blood clot in your leg.
Exactly. It is a wild contradiction when you really stop to think about it. I mean, we take the everyday miracle of our blood clotting perfectly to save us from a paper cut totally for granted.
Right.
But the idea of that same blood clotting inappropriately inside us is, well, it's terrifying.
And it absolutely should be.
Yeah.
I mean, the stakes of that microscopic process are incredibly high. So welcome to this deep dive into the fascinating and sometimes deeply paradoxical world of clotting disorders.
Yeah, we're really getting into it today.
We are, because what we are really exploring today is not a single disease. It is an incredible, high-stakes failure of equilibrium.
Right.
Our goal is to understand how your body's hemostatic system strikes this impossibly delicate balance between too much clotting, which we call thrombosis, and too little clotting, which leads to bleeding.
And it fundamentally changes how you view your own blood. To do this, we're looking at a really fascinating stack of sources today. We've got medical history papers spanning centuries, modern pathology journals, and the latest clinical guidelines.
Did a great mix of material.
Yeah, because, okay, let's unpack this. We tend to think of clotting as either a good thing or a bad thing. But based on the literature here, a clotting disorder, like a coagulopathy, is really just a failure of localization or timing.
Yes, exactly. Clotting itself is not the enemy. It is a highly controlled, strictly localized event.
So it's supposed to stay put.
Right. When you get that paper cut, the clot is supposed to form exactly at the site of the injured cells, plug that specific microscopic hole, and nowhere else. Then, once the vessel wall has healed underneath, the clot dissolves.
Okay, so where does the disorder part come in?
A disorder happens when any node in that intricate control system is deficient or excessive or just dysregulated. The disorder is simply the loss of control.
So before we can really understand how that control system breaks down, we have to understand the machinery that keeps your blood liquid when it needs to flow and solid when it needs to plug a hole.
Right.
Our sources break this down into 4 cooperating layers of hemostasis. And as I was reading through the clinical descriptions, I couldn't help but picture it as this highly coordinated, rapid response construction site.
That analogy actually works perfectly for the underlying biology. Let's look at the first layer, which we call primary hemostasis.
Okay.
When a blood vessel wall is breached, it immediately exposes the underlying collagen and a specific protein called von Willebrand factor.
Got it.
Almost instantaneously, platelets circulating in your blood recognize this exposed surface. They stick to it, they activate, change shape, and send out chemical signals to recruit more platelets to the site.
So the platelets are essentially like the emergency sandbags.
Yeah, exactly.
They rush in and form a loose plug within seconds to minutes. But sandbags aren't exactly a permanent fix against the pressure of pumping blood.
No, they would just wash away. Which brings us to layer 2, secondary hemostasis, or the coagulation cascade.
Right.
This is where plasma clotting factors, which are mostly enzymes, trigger each other in a highly specific sequence. Ultimately, they convert a soluble protein called fibrinogen into insoluble fibrin strands.
And those fibrin strands basically weave their way through the loose platelet plug, right?
Right, acting like concrete to stabilize the sandbags into a durable, hardened clot. It reinforces the whole structure.
Wait, if fibrin is basically biological concrete, what stops it? Like, if I get a paper cut, why doesn't that concrete just keep pouring and triggering until my entire arm solidifies?
That is the exact question that brings us to layer 3, the anticoagulant restraint.
The brakes.
Exactly. Your body has built-in natural brakes. These are proteins like antithrombin in the protein C and S system. They actively shut the coagulation cascade down outside the immediate injury zone.
So your body is constantly applying these brakes to ensure the clot doesn't spread from the cut into your healthy, uninjured blood vessels.
You got it.
Okay, so the sandbags plug the hole, the concrete sets the plug, the brakes keep the concrete from spilling down the street, and then finally we have layer 4, fibrinolysis.
Yes. Once the tissue underneath has completely healed, an enzyme called plasmin acts as the demolition crew.
Which is activated by something called tissue plasminogen activator, TPA, right?
Right. It meticulously chews the fibrin clot back apart, clearing the vessel out so blood can flow normally again.
This actually brings up a huge misconception I hear all the time. People always talk about taking blood thinners to prevent clots, like they are adding water to paint to thin it
Oh,
out.
I hear that constantly.
But looking at this four-layer system, blood thinners aren't actually thinning the fluid of the blood at all, are they?
No, they aren't. Blood thinner is a pure colloquialism and a slightly misleading one at that.
So what are they doing?
Well, the actual fluid viscosity, the thickness of your blood, it doesn't change one bit. What these anticoagulant medications actually do is interrupt specific steps in that construction cycle.
Oh, I see.
Yeah, they either block the enzymes pouring the concrete, or they inhibit the activation of the sandbags, the platelets. They are hacking the chemical signaling, not diluting the liquid.
That makes so much more sense. But figuring all of this out didn't happen overnight. I was reading in our sources about this German physician from 1856, Rudolf Virchow.
Yes, Virchow. He basically laid the groundwork for understanding this.
Right, because before him, doctors mostly assumed clots only formed because of mechanical injury, like a visible wound.
Exactly. But Virchow, who is often called the father of modern pathology, he wanted to know why bedridden or postoperative patients were developing these spontaneous deadly clots in their veins without any obvious trauma.
Oh, so he was looking at the too much clotting side of things.
Yeah, thrombosis. And he realized it comes down to three distinct factors, which we now call Virchow's triad.
Okay, let me see if I have these right from the deep dive material.
Go for it.
The first is stasis, meaning abnormal or sluggish blood flow.
Right.
The second is endothelial injury, so like hidden damage to the inner wall of the blood vessel itself.
Correct.
And the third is hypercoagulability, meaning something is abnormally pro-clotting in the actual chemical composition of the blood.
Precisely. And that triad is still the bedrock framework doctors use today. I mean, if you get a deep vein thrombosis after a long flight, you have stasis because you aren't moving your legs.
You aren't pumping the blood.
Exactly. Or if you have a clot from a severe infection, you likely have endothelial injury from the inflammation. So Virchow gave us the map for that extreme end of the equilibrium.
But what's wild to me is that historically, doctors didn't have the luxury of mapping out this beautiful four-layer system in a pristine lab.
No, definitely not.
They were forced to figure it out because they were reacting to terrifying, highly visible clinical disasters when the system failed in the other direction. The too little extreme.
Yeah.
Leading.
The clinical recognition of bleeding disorders actually goes back millennia. The Talmud, written in the 2nd century CE, contains an astonishingly early recognition of genetics.
Oh, right, the circumcision exemption.
Yes. It explicitly exempted a woman's third son from circumcision if her first two sons had bled to death from the procedure. That is the first recorded recognition of the inherited nature of what we now call hemophilia.
And it was a royal tragedy that really brought it into modern focus, right? Queen Victoria of the United Kingdom had a spontaneous genetic mutation for hemophilia B.
She did.
Which, based on our construction analogy, is a deficiency in factor IX, one of the key enzymes needed to pour the concrete.
Exactly. And because it's genetic, she passed this mutated gene down through her daughters into the royal houses of Russia, Spain, and Germany.
The whole royal family tree.
Yeah. The most historically impactful case was her great-grandson, Alexei, the heir to the Russian throne. He suffered from severe, agonizing internal and joint bleeding from just ordinary childhood bumps and falls.
Just from playing.
Right, because he was missing that one single factor in layer 2. The clot just couldn't stabilize.
And the disease was so poorly understood at the time that his desperate parents turned to Rasputin. And reading the sources, Rasputin's apparent, almost mystical ability to calm the boy's bleeding episodes wasn't magic at all.
Not at all.
He basically just kept the boy quiet and stopped the royal doctors from giving him aspirin.
Which is key, because we now know aspirin inhibits platelets, the sandbags.
So the doctors were actually making a bad situation worse by taking away the only functioning part of Alexei's clotting system?
It is incredible how a microscopic missing protein and a total misunderstanding of a common drug literally shaped global history and gave Rasputin fatal influence over the Russian court right before the 1917 revolution.
Unbelievable. Just a quick note from the medical history papers. Hemophilia B is also called Christmas disease, which I initially assumed was because of the holiday, but it's actually named after Stephen Christmas, the first patient to have this specific deficiency characterized back in 1952.
That is correct. And since we were discussing hemophilia, we really need to clear up a very persistent myth. You often hear that hemophilia only affects men.
Right, because it's an X-linked recessive trait.
Yes, it overwhelmingly affects males. because men have one X and one Y chromosome, so one faulty gene on that single X chromosome causes the full disease.
Right, and women have two X chromosomes.
Exactly. So the standard logic is that one healthy gene on the second chromosome compensates for the faulty one.
But the papers actually pushed back on that standard logic, right?
They did. Female carriers can and do suffer significant bleeding due to a biological process called skewed X inactivation.
Wait, what does that actually mean? Does the body just, like, turn off the healthy chromosome?
In a way, yeah. In female embryos, the body randomly shuts down one X chromosome in every single cell to prevent a double dose of gene products. It's supposed to be a roughly 50-50 split.
Okay, so half and half.
But sometimes it's highly skewed. If a woman's body randomly silences the healthy X chromosome in, say, 80 or 90% of her liver cells, where these clotting factors are made, she won't produce enough factor IXs.
Wow, so even with a healthy gene on paper?
She will experience severe bleeding symptoms, so it is absolutely not strictly a male-only condition.
That is fascinating. So we have this devastating royal history of too little clotting. But the discovery on the too much extreme is honestly one of the most bizarre medical stories in this entire stack of sources. It takes us from the Russian court to the American Midwest in the 1920s.
Ah, the great sweet clover mystery.
Yes! Farmers in the US and Canada were suddenly reporting this terrifying phenomenon. Their cattle were bleeding to death from incredibly minor scratches.
It's bleeding out of the fields.
And it turned out the culprit was spoiled sweet clover hay they were eating. A biochemist at the University of Wisconsin named Carl Paulink spent years trying to isolate the specific compound in the moldy hay causing this, and he discovered something called decumerol.
Right, and decumerol works by essentially starving the liver of its ability to use vitamin K.
And vitamin K is important because,
well, without vitamin K, the body simply cannot manufacture several vital clotting factors, specifically factors 2, 7, IX, and X. The concrete pouring cascade completely breaks down.
oh wow.
So Link's lab took this discovery and synthesized a much more potent version of the compound.
And its very first practical commercial application was literally as rat poison
Yes, it was.
because it caused the rats to bleed internally. They named it warfarin after the Wisconsin Alumni Research Foundation that funded the research, the literal rat poison to President Pipeline.
It is a remarkable trajectory. Warfarin only gained medical legitimacy as a human drug after it was used to treat President Dwight D. Eisenhower following his 1955 heart attack.
That is wild.
It went from a pest control chemical to saving the leader of the free world. And warfarin remains a critical, albeit difficult to dose, anticoagulant today. It deliberately tips the patient's equilibrium toward the bleeding side to protect them from deadly clots.
Okay, but this brings up a huge question for me based on the sources. Warfarin is basically hacking the system to push the seesaw from clotting toward bleeding, right?
Right, exactly.
But if the system is just a seesaw, well, can the seesaw snap? Like, can you have a disorder where you are clotting and bleeding simultaneously?
You absolutely can. And honestly, it is the ultimate proof that our clotting system is a highly interconnected dynamic web, not just a simple binary switch.
Wow.
Yeah. The condition is called disseminated intravascular coagulation, or DIC.
So I was reading the clinical description of DIC in the sources, and I have to admit, I was completely lost.
It's intense.
Yeah. You're saying a patient is hemorrhaging everywhere, but the root cause is that they are clotting too much? Walk me through how that is even physically possible.
I know, it sounds completely contradictory.
Yeah.
But here's the mechanism. DIC is triggered by massive, catastrophic events in the body. We are talking severe systemic sepsis or major physical trauma. Or profound obstetric emergencies, like an amniotic fluid embolism. These massive triggers cause the coagulation cascade to switch on throughout the entire vascular system all at once.
Oh, I see. So Virchow's hypercoagulability just goes into absolute overdrive everywhere.
Exactly. Instead of localizing to a cut, the concrete is pouring in every single vein. You are suddenly forming millions of microscopic clots everywhere in your body.
Which sounds bad enough.
It is, but because you are building millions of clots simultaneously, you rapidly consume all of your platelets and all of your clotting factors. You literally run out of the building materials.
So you use up all the sandbags and all the concrete?
Yes. And because the materials are entirely depleted, the patient begins to bleed severely from everywhere else.
That is terrifying.
They are bleeding precisely because they are clotting too much. DIC is a terrifying clinical scenario, but biologically, it completely dismantles the misconception that bleeding and clotting disorders are mutually exclusive categories. They are two sides of the exact same collapsing equilibrium.
If the body can do something that chaotic, how on earth do doctors even measure it? And more importantly, what happens when our medical models get it wrong? Because the history of medicine in these sources is full of us thinking we have the map, only to realize the actual territory of the human body is completely different.
That is a critical distinction. For decades, the entire medical field relied on the classic Cascade or waterfall model, first outlined in the 1960s.
Right.
This is the model with all the Roman numerals, factors I through 13, neatly lined up like falling dominoes in an intrinsic and extrinsic pathway that eventually meet in the middle.
Right. But the modern pathology papers we're looking at point out a major shift. In 2001, researchers Hoffman and Monroe published a landmark paper outlining the cell-based model.
A huge paradigm shift.
Yeah, they argued that clotting doesn't happen in isolated chemical pathways floating freely in the fluid of your blood. It happens physically anchored to the surfaces of specific cells, like injured tissue and activated platelets, in 3 overlapping phases: initiation, amplification, and propagation.
Which is much more accurate to life.
But wait, if the cell-based model is much closer to biological reality...
Because it requires actual physical cell surfaces.
Right. If it's closer to reality, why is the old 1960s Cascade model still taught in every medical school? Why are we still using a flawed map?
Well, because the old Cascade model beautifully explains our laboratory tests.
Oh, really?
Yeah. When a nurse draws your blood into a plastic tube and the lab runs a PT or an APTT test, they are forcing your blood to clot in an artificial environment. And the Cascade model perfectly predicts how those test tube reactions work.
But a plastic tube is not a living blood vessel.
Exactly. And that discrepancy leads to one of the most famous anomalies in hematology.
The factor 12 anomaly, right?
Yes. How does a plastic tube chemically force a reaction that a living cell doesn't? If a patient is severely deficient in factor 12, their APTT lab test will come back wildly abnormal.
So based solely on the test tube, they look like they have severe hemophilia.
Right. And the reason is that the glass or plastic of the test tube itself artificially activates factor 12 to start the cascade. But in real life, inside a living human, those patients don't bleed excessively during surgery or after trauma.
Wow. So their living cellular hemostatic system works totally fine without it.
Exactly. The old model fails to predict reality.
Which proves that a biologically plausible theory in a lab doesn't guarantee clinical success in a human. I was reading the clinical trial notes on a drug called Sigris, and I'm honestly confused.
Thickers.
It was synthetic activated protein C, right? Supposedly replacing the body's natural brakes during that terrifying DIC sepsis cascade we talked about. On paper, it looks flawless. Restore the brakes, stop the cascade, save the patient. Why did it fail so spectacularly?
On paper, it did sound like the perfect cure. It was even approved by the FDA in 2001 and written into global sepsis treatment guidelines.
So what happened?
Well, as the years went on, doctors realized it just wasn't saving lives. A massive follow-up trial in 2011 called Prius Shock proved it provided absolutely zero survival benefit over a placebo. It was pulled from the market.
But biologically, why didn't it work?
Because the biology of a dying patient is infinitely more complex than a single pathway in a textbook. Sepsis isn't just a lack of protein C, it's a chaotic, multi-system inflammatory meltdown.
Right.
Injecting a massive dose of one single break protein into a collapsing system doesn't fix the underlying chaos of the endothelial injury and the immune storm. There's a billion-dollar lesson that manipulating a pathway in an isolated model doesn't always translate to saving a complex living human.
And sometimes the manipulation goes wrong, not because of the biology, but because of human greed. The sources detailed this massive crisis in 2007 and 2008 with heparin, which is, another critical anticoagulant drug used in hospitals worldwide.
Oh, yeah. That was a chilling regulatory failure. Heparin is traditionally sourced from pig intestines, but a heavily adulterated batch entered the global supply chain from suppliers in China.
And it wasn't just an accidental impurity, right?
No, it was intentionally contaminated with a much cheaper substance called oversulfated chondroitin sulfate.
How did that even get past the safety checks?
Because it was chemically engineered to deceive them.
Wow.
I mean, the standard purity tests at the time were essentially just measuring the electrical charge and the molecular size of the compound.
Yeah.
So the counterfeiters engineered this cheap cartilage extract to exactly match that specific profile.
Just completely blinding the test.
Yeah, it looked exactly like heparin to the machines. But in the human body, it triggered severe, fatal, allergic-type reactions.
Yeah.
The disorder wasn't the patient's biology, The disorder was the chemical counterfeit. It forced a total overhaul of global testing standards.
If you're listening to this and wondering how all of this impacts you, well, we've talked about royal bloodlines, poisoned cattle, and billion-dollar drug failures. But this balance touches millions of normal lives every single day. Take daily aspirin, for example.
Yes. For decades, healthy adults were told to take a daily baby aspirin to prevent first-time heart attacks by permanently inhibiting those platelets, the sandbags.
But recent massive trials, like ASPRI in 2018, completely flipped that recommendation. We realized that for healthy older adults without prior heart disease, the risk of causing a severe internal bleeding event by constantly suppressing those platelets actually outweighs the benefit of preventing a clot.
We were tipping the seesaw too far.
Exactly. And if you've ever wondered why your doctor asks you a million questions about your family history before prescribing birth control, Virchow's hypercoagulability is exactly why.
Right, because birth control pills modestly raise your clotting risk.
And if you happen to have a genetic mutation like factor V Leiden, which, by the way, was only discovered in 1994, showing how new this science still is, that combined risk can push you right over the edge into a deep vein thrombosis.
We also saw this delicate equilibrium hijacked on a global scale during the COVID-19 pandemic.
Yeah, the sources touched on that.
The SARS-CoV-2 virus didn't just cause respiratory issues, it profoundly disrupted the coagulation restraint layer. It caused severe endothelial injury, triggering microclots in the lungs and other organs, even in young, otherwise healthy people.
So it was a real-time public demonstration of an infection pushing Virchow's triad into the red zone.
Exactly.
Yeah.
Not to mention the millions of people currently taking warfarin or newer anticoagulant medications who live this negotiation every single day. They have to balance their leafy green vegetable intake or monitor their antibiotics just to keep their blood in that Goldilocks zone, not too thick, not too thin.
Which brings us back to where we started. Every aspect of this, from Virchow's triad of flow, vessel wall, and blood composition, to the discovery of warfarin, to the delicate cell-based physiological reality of our hemostatic system, it all points to one central truth.
The localized balance is everything.
It really is. Every paper cut you survive, every long flight you walk away from is a testament to this miraculous microscopic equilibrium constantly recalibrating itself inside your veins.
It's pretty amazing.
Yeah. As we wrap up, our sources leave us with one lingering, incredible concept to chew on. We've seen how current drugs, like warfarin, systemically alter your whole body's blood composition, leaving you with massive whole-body bleeding risks.
Right.
But if the modern cell-based model proves that natural, healthy clotting only happens when it physically touches the surfaces of injured cells,
Yeah.
could the future of medicine be like smart anticoagulants?
Oh, wow.
Right. Imagine a drug that circulates completely harmlessly through your body and only turns on to stop a clot when it physically touches the unique molecular signature of a wound.
A world with zero bleeding risks.
Exactly. Where a drug only acts exactly where the paper cut is. Something to think about the next time you reach for a Band-Aid. Thanks for joining this deep dive, and we'll catch you next time.